So today we are going to be, talking about limits and derivatives too. And this is our second session. In the previous session, we have already talked about limits. And today we are going to be talking about continuity and differentiability. Okay. So before we begin with the theoretical part and examples, let's just quickly see what we are going to learn today. Okay. Firstly, very basic continuity at a point, left and right continuity over an interval, some algebra, okay, some special functions and discontinuities, intermediate value theorem, and continuity of composition functions. Okay, so this is one of the biggest things that we will do. Like the first one is continuity, and the second one is actually differentiability. Okay, just like the previous one, we'll also see certain connections between continuity and differentiability, and at a point or over an interval, how these things go, and also some algebra of differentiable functions. So these are the topics that we are basically going to cover today. So if you have any doubts regarding anything that we will be teaching today, please let me know in the chat box, and we'll just actually do some theories and some illustrative examples so that you people have a clear vision of what we are doing. So before I begin with the formal definition of continuity, etc., let me just give you an example which you have already done in previous day's class. Okay, so this was a graph that you were provided with and was supposed to find out the value of limit x tends to pi by 2 fx. Fair enough. So what you normally do is you just take the left hand limit, okay, from the graph, and also the right hand limit. So this is going to be 1. So this limit exists. So this is perfectly fine. But if you look at the functional value, this is the functional value, which is the value of the function at pi by 2. All right. So this is f pi by 2. This is actually 2, which is not equals to 1. So whenever we were talking about limits, this functional value didn't affect the existence of limit. But if you just look at the graph in general, this is going to affect the continuity of the graph. So I hope you understand what is the extra thing that we are going to take into account here whenever we are talking about continuity. So whenever you talk about continuity, apart from limits, the limiting value, functional value is also taken into account. Okay, so this is not continuous at pi by 2. Suppose this graph in general, even if it's not mathematically, what you normally mean by something being continuous. Okay, so probably if you look at this particular graph, so this was just going fine, and this was just going fine, and all of a sudden there's a jump. Okay, and then it continues again in this path. So fair enough, this was going smoothly. Again, there's a jump in this particular value at pi by 2, and then it's just again going smoothly down. Okay, so it doesn't affect the limit, but it affects the continuity, because for continuity, apart from the limit, we also consider the functional value. Now I hope where we are starting from is clear to you. So let's just go ahead and see the formal definition of continuity. Okay, first of all, we are going to learn continuity at a point. So we have taken a real function and any point x equals to a in its domain. All right. So this will be continuous at that particular point, provided this limit exists. Okay. So this is something we already know from the previous day's class. What will happen if the limit exists, the left hand and right hand limit, etc. And along with that, this limiting value should be equal to the functional value. So this is the extra condition that we are imposing on the function for it to be continuous. All right. So this is something you already know. Okay. So what happens when this limit exists? The left hand and the right hand limit should be equal. And not only that, it should be equal to the functional value, which is fa. All right. So if it is not continuous at x equals to a, it's said to be discontinuous at x equals to a. It's pretty simple. Just the reverse thing. If it's not continuous at that point, it's going to be discontinuous. Okay. So what we are going to do here is, just like the previous one, I'm going to take some examples, And the graphical examples are very easy to deal with, because you can see how this graph is behaving, how the function is behaving. If you look at the left hand and the right hand limit, you will see that the limit doesn't exist. So what was the first criteria that you need to follow? The limit should be actually there, okay? Then you check it with the functional value. If it doesn't exist, so obviously this is not continuous. So I hope you understand what it means to be continuous at a certain point. Here the limit is not existing, okay? Let's just take another function. If you look at this one, let's just first look at the limiting value. So it's perfectly fine, okay? But if you look at this, there's a gap in this particular graph. So it means that the functional value does not exist. So obviously this is not continuous, okay? So the first one is not continuous because of the fact that the limiting value is non-existent there. And for the second one, though the limiting value exists, the functional value is not there, okay? So this is not continuous again. So just some simple examples so that you know where it is continuous and when it is not. Let's just take another example. This limiting value is okay, but if you look at the functional value, as you see, both of them will exist, but they are not equal. Consequently, this is not continuous. And similarly, let's just take another example. So this is perfectly all right. The limiting value and the functional value, all of them are equal. Consequently, this graph is continuous at x equals to c. So I hope once you get these examples right, you will understand what are the basic requirements for continuity. Okay. So if you have any doubts regarding this one, feel free to let me know in the chat box so that I can repeat. All right. So first thing first, whenever you have any information about the function, whether you are given the function in general or you have the graph, first check the limiting value and also check the functional value. Okay. If both of them exist and are equal, then we say that it's continuous at that point. Okay. So next, what we are going to do is simply just take some other examples. Before that, let's just talk about left and right continuity. This is very simple. Every time when we talk about certain things, just try and see the name and how it suggests the possible definition. Left continuous, you already know that for the limit, the left hand and the right hand limit should be equal. Fair enough? So if the left hand limit exists and is equal to FA, then we call it left continuous. So you already know what we mean by the left hand limit. So this is something I just wanted to repeat. So whenever it's approaching A from the left hand side, so this is something very close to A but less than A. That's why we use the minus sign. And similarly for right continuity, you need the right hand limit to exist and be equal to the functional value. Okay. So this is what you have for the right hand limit. Fair enough. So right continuity and left continuity, I hope this is okay with you. There's nothing extra. Just whenever you see the name left or right, you understand which particular limit are we talking about. Okay. So let's just apply this thing and see how we can determine the continuity of a given function at a particular point. So this is what we are doing here. We have taken this function fx, which is defined as mod x cos x when x is non-zero and 0 when x equals to 0. We have to determine the continuity of the function at x equals to 0. So what is my first job at hand? The first thing first, we need to see whether the limit exists or not. Okay. First, we check the limiting value and then we see the functional value. As you can see, this is clearly the functional value, which is f0. Now you have to see whether this limit exists or not. So this is our first job at hand. Let's just find out the left hand limit and the right hand limit and see how these things go. Okay. So I hope now you understand why discussing limits in the previous session was very important, because now that we are going to be talking about calculus for a long time, so the next few classes are about calculus. So this is very important that you revise this one properly. So Great, I'm getting answers already. Very good. So if you people want to participate, that's absolutely amazing. Okay. So the first thing first, you go ahead and find out how this limit will look like from both the sides. X tends to 0 minus and x tends to 0 plus. Okay. So this is what we are doing here. Very simple. Just the way you approach for left hand or right hand limit. We have done these kind of sums before in limits, and similarly you go ahead and find out the right hand limit. Okay, so obviously this limiting value is there as well as the functional value which is defined at x equals to 0. So obviously whatever we were actually having as requirements, that is fulfilled. So this is perfectly all right. I hope this is okay with all of you. So this portion is something that you have already done in the previous class. So what you need to find out is the basic limiting values and also this functional value, and check whether they're equal or not. Okay. So if you have any problems regarding this one, please let me know. Otherwise, I think we'll just see some more examples and how it goes. Okay. So let's just take another application. If you still want to just have clear any problem regarding the previous sum, please let me know. So this is something I want you people to try. What you simply need to do is just find out the limiting value. So limit of this particular function when x is approaching 0, and also here you have the functional value as 7. Okay, so find out the limiting value, see whether it exists, and if it exists, whether it's equal to 7. Just try this one out and then we'll just see the results. Okay. So try and evaluate the limit first. If you see it's discontinuous or continuous. So if it's continuous, obviously the limit will be 7. Otherwise, if you are getting a different value for the limit, you also mention that in the comments box. Okay. Since you're already familiar with finding out the limits of certain functions, so just try this one out and then just see how the limiting value goes. Okay. Just try and find out the values. You already know some special formula. First of all, for e to the power x minus 1, then log of 1 plus something, etc. Just try and manipulate that and find out the limiting value. Because see, this is the reason why we wanted to repeat limit last day. Because whenever you're checking continuity, the limiting value should be evaluated first. Okay, and then you check whether it's equal to the functional value or not. Just try this one out. Okay, so I've got one answer from Shagnik. Shagnik says it's not continuous. Fair enough. So obviously, I hope the limiting value you got was different from the functional value. So first of all, let's just quickly see how you can find out the limit. Okay. So this is why it's very, very important that you know the basics of limit, right? So this is what we are doing. So now, obviously, this is one of the standard formulas that you have already done. And for this one, what you normally have is log of 1 plus something divided by that. Okay, so this is what we have done. So since this is 1 plus 2x, so we have taken this 2x here and adjusted it with 2. All right, so this is 1 and this is also 1, so you're just left with this. And similarly, you can just find out what happens when x tends to 0 plus. So that is why it's very, very important that you go ahead and revise, because this is one part where you have used a standard function and also for this one. But for both of them, since you need this x in the denominator, etc., so you have adjusted this x here along with this and also some adjustments of the constants. But this limiting value is there and the value is actually half. However, this functional value is different. Consequently, this is not continuous at x equals to 0. I hope this is okay with all of you. So just go ahead and practice more sums on limits so that you don't have any problems regarding the limiting value. All right. So let's just see another sum then. If you still have any problems, please let me know. Okay. All right. So first of all, as you can see that there's a portion of the value that we have taken here. This is a function where x is non-zero. All right. And this is when it's 0 and it is continuous at x equals to 0. So what happens is we have to find out this k. All right. So this is what you need to do. So what you normally do is you just find out the limiting value. Okay, what happens when limit x tends to 0 sine 5x by 3x, and you assign that limiting value to the functional value so that it becomes continuous. Just try and find out the value of k. Okay, I've already got one answer. Just try this one out and then we'll see. Okay. Very simple, just find out the limiting value, and for continuity, that is the value we should assign to the functional value. Okay, so I'm getting answers. Great. So I hope this is okay and you understand why repeating limits was a good idea, because that is the first step that you need to take towards evaluating, or determining continuity, etc. So great, you people have said that it's 5 by 3. So let's just see. This is what you have. Some simple adjustments of the constants, but this is very, very, important, because the way you adjust the constant, that will eventually provide the value. Okay. So once you get this limiting value, this should be equal to the functional value. So obviously this is what you assign to k. So this is absolutely all right. Okay. So I hope this is okay with all of you. So now, once you understand these things, I think we'll just move on to the next portion. All right. So we have done 3 types of sums. The first one where it was continuous, in the second one where it was not continuous, and we have also taken another sum where we had the opportunity to define the functional value so that it becomes continuous. Okay. All right. So once we are done with continuity at a point, now we are going to talk about continuity in an interval. But before you go on to the formal definition, etc., I just want you people to understand one simple example. I have taken the greatest integer function here, which is the box function or the step function, as you people are familiar with. So what I'm doing here is I'm just taking box x at x equals to 2. You can take any other integer. So let's just see what happens around this particular point. Since we are familiar with the continuity at a point, so this is what we are going to explore now. Okay. So what happens when it approaches 2 from the left hand side? Obviously, the value will be 1 because this is very close to 2, but still less than 2. So this value is going to be 1. But if it approaches 2 from the right hand side, this is something more than 2. So this is actually the box function's value. Okay. So obviously this limit does not exist, and consequently we don't even talk about the functional value, which is actually 2. Okay. So you see that if you take any other integer, it's going to be discontinuous. But even previous day we were talking about, certain limits. Suppose limit x tends to 5 by 2 box x, you'll see that that limit will exist and that is continuous. So if you take any other non-integral point, it is continuous. As you know, the domain of the box function is the entire real number line. So it's pretty obvious whenever you're considering a function, it might happen that it is continuous at some points, whereas discontinuous at others. So apart from talking about continuity at a point, it's very important that we extend the concept and talk about continuity in an interval. So I hope this is okay with all of you and you understand why we are expanding this concept, and then we are just going to see the formal definition. Okay, so whenever you talk about intervals, you have different types of intervals like open interval or closed interval or half open, half closed, or semi-open, whatever you say. So these are the three types that we will consider. So first of all, we are just starting with continuity in an open interval. So let's just see the definition. This is very, very intuitive and very obvious, in the sense that whenever you're saying that it's continuous on the entire interval, it's going to be continuous at each and every point. Okay, so you take any point from the interval AB and it is going to be continuous there. So as you see that in the definition, from interval we have come down to points. Now you know what is there for continuity at a point. So this is the definition that we are going to explore. So what is there for continuity at a point? So if I take any arbitrary point from the interval AB, which is the open interval, it should be continuous. So consequently, we have used the definition of continuity at a point. Okay, so this is very, very intuitive, and I hope this is okay with all of you. So, all right. Now, let's just move on to the next part, continuity in a closed interval. So here, this is how this will look like. So what is the extra thing that we have taken here? Apart from this open interval AB, we now have the extremities included. The extremities being A and B, all right? So the first thing first, you just consider the corresponding open interval, all right? So this should be continuous on that open interval. And apart from that, since we are also talking about the extremities in the closed intervals, this should be there for A as well as B. But just now notice one thing, we have taken A plus and B minus, okay? If you just look at the entire A to B portion, obviously in this particular interval, it can approach A from right. So that is why we have this plus sign. If it's approaching from left, if it's not in the interval, we are not even considering this, okay? So this is the right hand continuity or right continuity that we are using for A. And for B, it's approaching from left. So obviously, that is why we are using the left continuity. I hope this is okay with all of you. Otherwise, if you have any doubts, feel free to let me know in the chat box. So whatever we did for the open interval, along with that, we are also considering the extremities. But for extremities, we have the right hand and the left hand limit accordingly. Okay. So this is what you have. Now this is again from whatever you have learned in terms of, closed or open interval. You can extend that and find out these two types are there. So here A is included. So we are actually going for AB open interval as well as the A part where it's like the right continuity. And also for this one, apart from open interval AB, we are talking about left continuity at B. I hope this is okay with all of you. Still, if you have any problems, just write things down if you want to, or make a note, anything that is convenient. Okay. If you have any doubt regarding this one, please let me know in the chat box. And even if we move on, and sometimes, whenever we are talking about some other problems and you just remember that, okay, I cannot understand this one now, also then you can let me know about your doubts. So these basic definitions or conditions are very, very intuitive. So even if you forget just some basic intuition, and I think you'll be good to go. All right. So once we are done with the definitions, obviously, let's just go ahead and explore some other things. But before that, I'm going to tell you about two more things. The first thing we have taken here is actually continuous function. When we say that it is continuous, whenever it's entirely, continuous in its domain. So since we have already talked about continuity in an interval, here the interval is the entire domain. Okay, so when we talked about the box function, it is continuous at certain points, except for the integers, it's continuous everywhere. But for a function to be continuous in general, it should be continuous at each and every point of its domain. Okay, so this is very, very important. Everywhere continuous function means it's continuous on the entire real line. So make sure you understand the difference between these two. Okay, they might seem a little similar, but they're not exactly the same. I can give you an examples, like, so if you're considering log x, ln x, so obviously you know that there's a restriction on x, that it has to be positive, x is greater than 0. So log x is actually continuous in its domain. But if I just consider another function, suppose the constant function, it's continuous everywhere because its domain is nothing but the set of all real numbers. Okay, so whenever there's a function, it has its domain, it's continuous everywhere, so it's perfectly all right in its domain. But for a function to be everywhere continuous, the domain should be R and it should be continuous there. So I hope you understand the difference. We'll do certain sums in future, or some basic results, etc. Then I'll just define this once again. Okay, so I hope this is okay with all of you, and let's just go and see some applications. All right, so we have to discuss the continuity of the function in this particular function that we have been provided with. Now this is very, very important. Previously we were talking about a function and its continuity at a point. Sometimes you are just given like just evaluate or determine the continuity at this point or at that point, or etc. Here you have to determine the or discuss the continuity of this function in general. So whatever be the domain of the function, it should be actually discussed in the entire domain. All right. Okay. Shomojiti says it's not continuous. So other people, if you want to try this one out, it's absolutely all right. It's not that, I can just show you the solutions right away. If it's something that you want to just, kind of explore and see how it is. Okay. So this is something you can do, obviously. And in fact, I'll prefer that. So if you people want to try, so this will be good. All right. So, okay. So not continuous. I'm getting a lot, some answers. Great. Okay. Now there's an important point that I would like to raise here. If you look at the particular definition of the function that you have been provided with, it is pretty obvious that x equals to 4 is actually the point of discussion. Okay, so as you talked about, as I just just told you an example of the greatest integer functions, etc. I told you that, see, these are the integral points. They are the points where things are causing some difficulties. So let's just go and examine that there. So whenever you see certain function changing its behavior around a certain point, so obviously that's the point that you should examine for continuity. As you know that mod x minus 4, this is something that we are going to discuss now. So you know that this function will change its behavior around 4. Fair enough? So I'm just writing this one so you understand what I'm talking about. So around 4, this is going to change its behavior. If it's less than 4, this is actually a negative number. So it's coming out as positive, which is 4 minus x. And consequently, if it's more than 4, so it's just kept as it was. Okay. So we redefine the function. Very, very simple. All right. So once you're done with this, you just look at one thing. This is something we are going to be talking about like in general. A constant function is everywhere continuous. Similarly, this is also a constant function. We'll talk about this. This is a standard result. A constant function is continuous everywhere. So if you look at the first two parts, it's continuous. So it's perfectly all right for x less than 4 and x greater than 4. So our question is what happens at x equals to 4. So once you figured out these possible points where the function is changing behavior turn and it can affect the continuity of the function in those points, so obviously now we are going to be discussing about them. Okay, so from the interval we are again down to continuity at a point, so you know how to check that. Very simple. This is -1, but you see this is +1, and obviously this is not going to exist. The continuity is not there at x equals to 4. The reason being the non-existent limiting value. Okay, so you shouldn't even check that, but I've just written that for clarity. It's okay if, even if you don't check this one, because the limit doesn't exist at all. So I hope this is okay with all of you. So it's continuous everywhere except for x equals to 4. So if you consider the entire number line, suppose this is 4, so less than 4, we said, okay, fair enough, this is -1 and it's continuous. This is +1, this is continuous. But at x equals to 4, no. Okay. So I hope you understand this is the entire real number line except for this 4. All right. So I hope you understand what we mean by continuity in an interval. Okay. We'll just do okay, first of all, let's just see some algebra of continuous functions and then we'll just move on to more and more examples. Now, again, this is very simple and not difficult things that you should not be able to follow. Already we have talked about algebra of limits, algebra of functions, etc. Similarly, we are going to talk about algebra of continuous functions. All right, so what we have done here is we have taken a couple of continuous functions at a point. Now we are talking about a point, and alpha is any real number. Fair enough. So f plus g, f minus g, the scalar multiplication, product, quotient, all of them are continuous at x equals to a. So this is basic algebra of continuous functions. So if you take a couple of continuous functions at a particular point, so their product, their quotient, their added summation or their difference, all of them will be continuous at the point, as well as the scalar multiplier. All right, so these are very, very simple. What I'm going to do is I'm just going to prove the first one with you and see how the proof goes. It's very simple and intuitive. Just uses the basic definitions, etc. But once you see the proof, certain things will be clearer to you how you can apply some results in general. I'll ask you people to go ahead and try the other proofs, because even if it's not very important from the point of view of examination, this will give you a very clear idea about the basic things that you should need to know. Okay. All right. So this is the first thing we have taken here. So this is the given point that we are going to explore. So this is what we have for any function which is continuous at x equals to a. Now you have to show that f plus g is continuous at x equals to a. So I'm just starting with the limiting value. Okay, I have to show that the limiting value of this particular function is going to be same as the functional value. Okay. Shomojyoti, you're just saying, can we say that for left limit, the denominator is negative and the positive? So if you're talking about the mod, mod x minus 4, yeah, this is something you can do, but at the end of the day, it's not about only being positive or negative, okay? If you are also seeing the numerator, if it's changing, it's the ultimate value that matters. If the numerator is not changing and the denominator is different from one another, then it's perfectly okay. All right. So otherwise, you see sometimes the denominator is changing and the numerator is changing. So together it does not affect the entire change. So that is something you should be a little careful about. If you know that this is the reason behind discontinuity, it's perfectly fine. But whenever you're checking this one, so you check these things properly. That's it. So for the previous one, this is kind of okay, but this is something you should be more aware of, because also the numerator is pretty disturbing, like this mod function, etc. So I hope your queries answered. All right. So this is what we have taken. What we need to do is, this is the information that we already have. And also we need to show that this is continuous at x equals to a. So for continuity, what we normally do is we show that this limiting value should be equal to the functional value. So see, what we have done here is we have applied simple algebra of functions. All right. So next, algebra of limits. So this limit. Okay. Now you know the individual values, and then again you apply algebra of functions. So this limiting value is same as the functional value. As you see, this is very, very simple when it comes to the proof, some basic definitions, but you actually understand how all these things are interrelated, and how we can use the algebra functions or limit to build on the base of algebra of continuous functions. All right. So still, if you have any problems, feel free to let me know in the chat box. So I'll just do some very, very simple examples so you know how to apply them. They're not individually something that you need to prove or, use a lot in general. But whenever there are certain sums where you know the individual components to be all right, then you can add them or subtract them or take the product, quotient. We'll do things like this, but just let's see how we can explore that. Sin x and cos x are trigonometric functions, and they're continuous everywhere. So this is also a standard results that we are going to explore later. So in general, it's continuous at x equals to pi. So if you just take their summation, it's going to be continuous. So this is not very difficult, but this will actually give you an idea that sometimes when you are judging the continuity of a function, okay, which might be a little complicated, like some products or quotient or summation, etc. If you look at the components individually and judge their continuity, then probably you will have certain way out. Okay. Another example, very simple. X is the identity function. This is a trigonometric function, and this is a polynomial. Actually, all of them are continuous, and we'll actually talk about these things for the time being. Just take them as some standard results. All right. And also this is non-zero. Now this is very, very important. Whenever you're taking the quotient, it's an important topic of discussion that this particular denominator should be non-zero. So you know that at x equals to 0, it's obviously non-zero. So we have taken the product of x and sin x, along with that a quotient with x square plus 2. So this is how you can basically apply the algebra of continuous functions. So if you individually examine the nature of the functions, you will actually see how we can apply the algebra of functions to construct some continuous functions. Fair enough? All right. So whatever we have learned so far, it was for continuity at a point. Now again, we are extending this idea to domain. But this is one thing that you should notice. We have taken the common domain, okay? Now this is very, very important. Doesn't matter, what we are talking about in terms of algebra of continuous functions, anything. Okay, at the end of the day, they are functions. So whatever they should follow as for being functions, this is something that you should never, let go of. Okay. So at the end of the day, whenever we are talking about certain, summation or subtraction, whatever you do, or product or quotient, at the end of the day, it should be defined. Okay. So you take their common domain. So the same thing, just not going to repeat this one. It's very simple. Just extend the idea from a point to the domain. All right. But again, this is important. So I hope you understand this part. We have taken the domain except for the point where this gx becomes 0. Okay. So I think it's should be okay with all of you. So that's it. Now, this is something that we will do, as I have told you on many occasions, that we will do while doing some examples, etc. I told you that constant function is everywhere continuous, or this is a trigonometric functions, etc. So sometimes instead of just checking the continuity of functions all the time using limits or functional value, we are going to talk about the continuity of some special functions that you always deal with, certain functions that you always deal with everywhere. So if you know the continuity of them, then there are certain steps that we can avoid. First result that we are going to do here is a constant function is everywhere continuous. Now this is very, very important. I'll just do a couple of proofs with you so that you people understand how to approach. You will get these proofs everywhere. These results are enough, but if you do the proofs, you will at least see how these things go. Okay, we'll do a couple of proofs, and the rest will be I'll just state the results. So this is how a constant function looks. Pretty simple. What you need to do is you just go for the limiting value as well as the functional value. So this is the domain. So that is why we are saying everywhere continuous. I'm taking any arbitrary point. For it to be continuous in the entire domain, it should be continuous at each and every point of the domain. So arbitrarily, I have taken any real number A. Fair enough? So let's just see how this limit will go. It's very, very simple. What is fx? Fx is nothing but c because it's a constant function. So as you see this particular function, it has no effect from x tending to a, etc. So similarly, if I take this particular value at the particular point, the functional value, that is also c. So obviously this is going to be continuous. Okay, very, very simple. The left hand limit, the right hand limit, the functional value, all of them are c because it's constant. And also if you look at the graph, you can clearly see how this goes. Okay, so it's pretty simple. A constant function is everywhere continuous. So when I said that, okay, this is coming out as -1 or +1 in this particular segment, without even thinking about the limiting value or the functional value, we say that it's continuous. So I hope this is okay with all of you, but still if you have any problems, please let me know. So this is our first result. A constant function is everywhere continuous. So in the entire real number line, okay? The next result, the identity function is everywhere continuous. Again, we are going to just explore the very, very simple idea of continuity. This is the function. This is any possible real number. This is what you need to evaluate. Simply put the value of the function, which is fx, that is x. So basic thing, if you know that the limiting value, if you know that if you just substitute the limiting value and it exists, then this will be the value that we are requiring. So if I just substitute x equals to a, this is not causing me any problem. So similarly, this is also a. So this is perfectly all right. Again, if you see the graph and it just goes on, so this is also continuous. So these are certain small proofs that I wanted you people to understand so that you know whenever we state certain general results or standard results, what is the reason behind that. So the first one you talked about was the constant function. Then you have the identity function. So next we are going to talk about the polynomial function. Okay, it is also everywhere continuous. So this is how a polynomial function will look like. Then see, this is the part, this is actually the constant part. Okay, if I just take this part only, this x, the rest is not there, and also a1 is 1 and a0 is not there. So this is the identity function. All right, so we have taken some basic things like something with degree 0 or degree 1. Here we have taken a general polynomial. Okay, so this is everywhere continuous, and you can just simply prove it using mathematical induction. We're not going into the proof now. I'm going to state some results, and as I have shown you how the proofs will go, so I hope you understand where these standard results come from. Okay, as a corollary of this, we'll do some rational functions. What is a rational function? This is how a rational function should look like. It's the quotient of two polynomial functions, okay? And also the denominator is non-zero. So as you know that polynomial functions are continuous everywhere, so gx and hx will be continuous as well. So whenever you take their quotient, now you see we are using the algebra of continuous functions. All right, so this is also continuous, but make sure this denominator is non-zero. So I hope this is okay with all of you. So this is the third standard result, polynomial. As a corollary of that, we are getting the rational function. And again, everywhere continuous, because the domain here is nothing but the entire real number. That's why we are saying it's everywhere continuous. All right. Okay. Some more results. The modulus function, again, the mod function is everywhere continuous. As we said that we are going to explore the continuity of the functions that we see a lot around us. So this is another function. There's a result that you have. So I'm not going into the detail of the proof, but I'm going to give you the outline so that you can pick on certain good points. So there's a result that we are going to use here to prove this. It says that if f is continuous on its domain D, then mod f is also continuous. Okay. So this result will easily help you to prove the result that we have stated here about the modulus function. You know that this is the identity function, so it's continuous. Obviously, its mod will be also continuous. But there's a question that arises whenever you see a result. The obvious question is the converse of this result true? What we stated was if f is continuous on its domain D, mod f is also continuous. So I want you people to just tell me whether you think the converse of the result is true or not. If it is true, then give me a general logic, or if it's not, you can provide me with a counter example. So I hope this question is clear to you. And also this proof, we have used a result, the rest is pretty simple. But now I'm talking about another point, whether the converse of the result is true or not. So let me know what you think about the converse. Anything that you want to say about the converse of the result, you can just let me know in the chat box if you have some counter examples where you can see that not happening, the converse is not happening, or any other thing that you have observed. Just take a moment, and if you people want to contribute to this particular answer, feel free to use the chat box, or you can speak up. If it's a long answer, it's better that you people speak up. All right. We'll just try and construct an example, actually a counter example, where we will show that mod f is continuous, whereas f is not continuous. So this converse is not true in general. So as you see, let's just take an example. Okay, this is how you have defined fx. So it is 1 whenever it's an integer. Okay, otherwise for any other real number we have taken this as -1. It's pretty obvious that if you take any integer, this is discontinuous. So suppose I'm taking an integer, it's approaching from this left side, it's very close to the integer but not exactly the integer, so the value will be -1. Similarly, in this portion the value will be -1, but the functional value is 1 for the integer. So it's discontinuous, more of like the box function, how we have problems in the integers. But whenever you take the modulus is actually 1 for everything. So which is a constant function and obviously continuous everywhere. So as you see, this result is something that we have used for proving the fact that the modulus function is continuous everywhere, but the converse may not be true. I hope this is okay with all of you. So that's it. So far we have talked about The constant function, the identity function, polynomial, rational, and modulus. These are all standard functions that you already know about. I'll just quickly tell you about certain continuous mode functions, some, standard functions. Exponential function is everywhere continuous, and as a corollary, e to the power x is everywhere continuous, okay? Because I'm just putting a as e, which is obviously greater than 0, etc. Now, this is very, very important. The logarithmic function, I told you people that there's a difference between everywhere continuous, which is obviously this R, okay? The set of all real numbers. Whereas it is in its domain, because you know that there are certain restrictions on log x, okay? So this is one of the things that I wanted you people to figure out, that what is the difference between continuous and everywhere continuous. Trigonometric functions are continuous in their respective domains, and also inverse trigonometric functions are continuous in their respective domains, okay? So we have talked about the continuity of some special functions. So whenever you are supposed to judge some continuities, which we have already done, you don't have to go for the basic definition of continuity. You can simply use the standard results and talk about the continuity, okay? I hope this is okay with all of you. And we'll just simply move on to the next slide then. You still have a problem, please let me know. Take a good note of all these possible standard functions which are continuous, because we'll use this to prove the continuity at some other points, okay? So very simple continuity that we have done here. Now I'll just say the first part, and then I'll talk to you about the problematic points, okay? Sine 2x is trigonometric function, x is the identity function, their quotient will be continuous. So if you look at this particular portion where x is less than 0, that's it. So you didn't have to go for the entire limiting value, this value, that value. Nothing matters. Just use this continuity of some special functions and you're done for x's, for any x which is less than 0. All right. Take this one. This is a polynomial. So obviously for x equals to x greater than 0, it's sorted. So what is our point of discussion? Where the function changes its behavior. Now from the entire real number line, we are down to a point which is x equals to 0. Now we are going to go ahead and use the limiting value and the functional value, etc. So I think I've got already got one answer. So I want you people to just try and say whether you think it is continuous at x equals to 0 or not, okay? The rest of the portions, we didn't have to do anything at all. We have used some basic continuous functions and proved that this is continuous for x less than 0 or greater than 0. Now here what we need to do is we have to examine the continuity at x equals to 0. So just try this one out and let me know whether it's continuous, okay? At x equals to 0. Just find out the corresponding limits. Okay, you're saying, all of you are saying that it's continuous, great. So I hope you understand, whenever we are talking about discuss the continuity of this particular function, you have to discuss it for the entire domain of the function. But again, the entire domain is a large segment. So what we have done is we have just zeroed in on some basic points where it might cause trouble. The rest can be taken care of using the general standard functions that we have done. So what's our job at hand? Simply find out. So x equals to 0 is the point of discussion here. Very simple. You take this one, adjust the basic constants. See, this is very important, okay? Since this is less than 0, very close to 0 but less than 0. So this is the definition of the function that we are going to use. This is very, very important whenever you have this left-hand limit. This is close to 0, but still less than 0. So this is what we have used. Rest is pretty simple because you are aware of the sin x by x, etc. But adjust the constants properly. For greater than 0, obviously we have used this particular definition. All right. So simple. Limiting value is there. For the functional value, which one is having the equality? This is the one where it includes 0 as well. So obviously this is 2. So it's perfectly all right. So it's actually continuous at x equals to 0. So basically it's continuous everywhere. Okay. I hope this is okay with all of you. So you understand how we can apply these special continuous functions to reduce some of the calculations and just come down to the points where it's causing trouble. All right. Now, this is one topic that is very, very important. And if you have any problems regarding this topic, feel free to let me know, because this is a little different from what we have done so far. And let's just see some examples first, okay? Since we have talked about the continuity of a function at a point, it's very important. So just also discuss about discontinuity. As you see that I have taken 3 examples here. All the examples suggest that the function that is there in the graph is discontinuous at x equals to c. Fair enough. But if you see the reason behind discontinuity, let's just explore that. The first one, obviously you can see that the limit is not existing, okay? So if I just go for the left hand limit and the right hand limit, you can see there's this jump and obviously it's not equal. For the next one, okay, there's no problem with the limiting value, but the functional value is absent. All right, just see the next one. Okay, this is all right. Also there's this functional value, but they are not equal. So whenever a function is discontinuous at a particular point, it might happen that there are certain different reasons behind this discontinuity. Now these different reasons will actually pave our way to the different types of discontinuity. I hope this is okay with all of you and you understand where we are picking up from whenever we are talking about a new topic. You know where we have started from. All right. So the first type is removable discontinuity. All right. So what are the possible reasons here? Suppose we have got a function which is discontinuous at a particular point. So whenever it's called the removable discontinuity, what happens? The limiting value exists. Okay. So there's no problem with the limiting value, but this is either not equal to the functional value or the functional value is not defined at all. So if you remember in the second case, this was okay, but the functional value is not defined. In the third case, it was not equal to the functional value. So all these things are actually categorized under removable discontinuity. Now, I normally ask you people to look at the name and just get some clues from there. So this is what we are going to do. So we can redefine the function in such a manner that it becomes continuous. So if you remember, we actually did a sum that you people point out that k will be equals to 5 by 3. Because if you remember at x equals to 0, the limiting value was 5 by 3. Then you were asked just, find out the value of k so that it becomes continuous. So if you have the limiting value, you can assign that particular value to the functional value as well so that we can make it continuous. So this continuity is actually removable. We can define the functional value in such a manner that this discontinuity goes away. Okay. So suppose you know that the limiting value is 1, but the functional value becomes 2. So what you do is you redefine the function where the functional value is 1. Or maybe just take another example where the functional value is not defined at all. Okay, it doesn't exist. So what you do is you separately define it as 1. So this is what you do. I hope this is okay. Now, since there are 2 reasons, then we have again two types of discontinuities, removable discontinuities to be precise. The first one is missing point discontinuity. Again, look at the name, missing point. So FA is not defined. So the graph was going perfectly well, there's no problem with the value of the limits, etc. But all of a sudden this functional value is missing. Okay, so this is why it's called the missing point discontinuity. What is the other possibility? It's not equal. So that is called the isolated point discontinuity. So it was just being continuous. Okay, the left hand and the right hand limit was same, but all of a sudden at this particular point the value was somewhere, you know isolated, and it was not there in that vicinity, and it was not equal with the limiting value. So whenever you see these kind of names of the different types of discontinuities, I hope you understand what they mean. And if you just try and just see them step by step and what they mean and what is the possible reasons, things will be easier to deal with. I hope this is okay with you. So this is a part that you should not miss out on. This will necessarily exist. Okay. So there's no problem with the limiting value. The entire problem lies in the functional value, and that's why we can redefine that to make it removable. We'll do a couple of examples, and I'm sure it's just going to give you a lot of clarity. Very simple examples. Now this is very important. You know that box X or binary box X, they cause trouble at a particular point, which are integers. Okay, if you see this entire open interval, so the extremities are not included. So what can be the possible point? The possible point can be 1. So this is our first observation. So if you have any problems regarding this one, please let me know. So this is my first observation. If you look at the entire open interval, the only point of discussion should be x equals to 1, because all these box x things will actually trouble you there, the integers. So this is our first point of discussion. So I want you people to try and find out the limiting value and assign the same value to the function so that it just becomes continuous. Okay. Firstly, try and find out the limiting value. Just let me know the limiting value, what happens when x tends to 1, and how this limit goes. Just try and find out the value. Okay. I hope the first point is okay with you all. Why we are checking the particular point x equals to 1. If you still have any doubts, please let me know so that I can clarify. So this is the first point that is under observation. Okay. Have you found out the value of the limiting function? Limiting value of the function. Okay, let's just see how we can explore this one. So I hope the first point is clear with you all. And by the time, if you get the value, please let me know in the chat box. All right. If you look at this particular interval, the only point of consideration should be the integer, which is 1. Okay. And see the open interval, obviously the 0 and 2 are not included. Very simple. If something is, sorry, this should be a box. All right. It's very simple. Something which is less than 1, obviously that should be having the box as 0. And this is something a little more than -1. So the box is -1. Consequently, the limit is -1. So if you people have any doubts regarding the limits, please go ahead and revise. But because for continuity, again, you need the limiting value, for which you need the concepts of limits to be clear. Okay. Similarly, we can find out the right hand limit. Okay, so what was the first condition? Now this is very, very important. Okay, the first condition was this should exist. Okay, if the limiting value exists, then we will talk about the functional value. What do we do here? This is what we have. What is f1? Just put the value. You see, there it is. It's just causing the problem. So obviously what we are going to do is we are going to redefine f1 as -1. Okay, so see, there's a removable discontinuity of the type isolated point. Okay, so the limit is existing, the functional value is existing, but they're not equal. So we redefine the entire thing. So as you see, from 0 to 2 up to 1, or from 1 to 2, this open interval, there's no problem. But for x equals to 1, we have assigned this value so that it becomes continuous and equal with the limits. I hope this is okay with all of you. So the first thing first, you just figure out which point to consider for the discussion of continuity, then find the limiting value. If it exists there, then only it's removable, and then try and find out the functional value accordingly. All right. So that's it. Let's just do another application. Very simple. As I've told you, just find out the possible point where it can cause problem. What is the point that can cause problem? Obviously, it is x equals to 4. So first of all, try and find out this limits. This is something you should do. Tell me the the limiting value. This is basic rationalization, etc., that you have already done in the previous class. So just find out limit extends to 4, this particular functional value. I hope this is okay why we have taken 4, and the rest is pretty simple. First of all, try and find out the limiting value so that we can assign the same value to the functional value and get the continuity going. Okay. Okay, I think I've already got one answer. Let's just see some more answers, and then we will talk about how we can redefine the function. Boivav, you have raised your hand. Do you have any query? or
Ma'am, can
you can,
you explain the previous part again?
which one? The previous question or
The
the
previous
four?
question.
Okay, okay, okay. I'll just go back to the previous question and just let me know if you are having any problem. So first of all, you can stay connected via the audio. So if you look at the entire interval 0, comma 2, okay, the function we have here is box x plus my box of minus x, okay. This is the function that we have. As you know that the box function causes trouble in integral points, okay. So that is why if you look at the entire interval where we are supposed to judge the continuity, the only troublesome point might be 1. So I hope this is up to this point, it's okay. So that is why we are considering the continuity at x equals to 1. So for the continuity, what we need to do is, in general, we go ahead and find out the limiting value. So this is what we have done at first, okay. So this is the left hand limit. So this is nothing but h tends to 0 if 1 minus h. So we have just put the value. So if you look at the number line, okay, suppose this is 1, this is 0, this is minus 1, etc. Okay. Now what is this? This is 1 minus h. So this is somewhere here, very close to 1. So what is the box? The box is 0. So that is what we have put here. All right. And this is actually box. Okay. So this is minus 1 plus h. So minus 1 plus h means something more than minus 1. So obviously that box will be minus 1. Okay. So that is why this is the limiting value. Similarly, you can go ahead and find out what happens if this is 1 plus. So obviously this will be 1 plus h. This will be like minus 1 minus h, etc. So once you're done finding out the limiting value, this is what you have as the limiting value, okay. So this is the first condition for removable discontinuity, that the limiting value exists, okay. Once you're done with the limiting value, let's just go ahead and find out the functional value. This is a functional value. Just put f x equals to 1. So the functional value is 0, which is not equals to the limiting value. So obviously it has an isolated point discontinuity. So what we do is, since this is causing the trouble, we redefine the function. So if you take 0 to 2, this is perfectly all right. Okay. But just this 1 is causing trouble. So you are taking 0 to 1 open bracket and 1 to 2. So everything is there except for 1. And just for 1, we have redefined the value as minus 1. So that whenever you get this limit as minus 1, it doesn't cause any trouble with the functional value. Okay. Is this okay with you? Then let me know. Otherwise, if you have any other problems, then I can repeat. Is this okay? Okay, okay. So I hope you understand how to find out the point where the continuity is worth discussing. So let's go to the next one. So this is very, very important. First of all, try and find out the limits. I don't know why you people couldn't find out the limit, because this is very, very simple. This is like, if you just find this one out, this is very simple. Root x minus 2 and root x plus 2. Very simple factorization. I don't know what caused you some trouble. That's it. So this gets cancelled. All you have is 1 by root x plus 2, which is 1 by 4. So that is the limiting value. I hope this is okay. And again, I have told you people, you see this, the concept of limit is very important here. So if you're not comfortable with the walking out of the sums that we have done, go ahead and revise. Here the point is, it's actually a missing point discontinuity. This limit is there, however, you don't have f4. Why? Because if you simply put x equals to 4, you see that this is not defined. So how do we define that? It's very, very simple. This is perfectly all right. So from 3 to 4 and 4 to 5, only 4 is missing here. So we have taken this extra effort to make this continuous. I hope this is okay with all of you. So if you have any trouble regarding this one, please let me know. And again, go through the steps, find out the point where it might cause a trouble, find out the limiting value, then just assign the functional value. If it's not continuous at that point, just go ahead and assign the value. Okay. All right. The next one is non-removable discontinuity. So what is the condition? This is the condition that the limit does not exist. Okay, so if the limit doesn't exist, we can't do anything about the functional value. So the limit has to exist, the functional value has to exist, and they should be equal. Shomojyoti, which one didn't you understand? The previous one? All right. Okay. So you told this was like 1/6, but just evaluate the limit properly. This will come out as 1/4. Okay. So just check the calculations. So is this okay with you? Or if you have any other trouble, you can also unmute and speak, because I exactly didn't understand your query. Is this okay? All right, just go ahead and evaluate the limit. It's very simple. I have factorized the denominator, so you will see that this root x minus 2 is getting cancelled. And probably when you just did root x plus 2, you make sure this root 4 will come out as 2. So this will be 2 plus 2, 4. So f4 is not defined, so that's why we have assigned this value. So I hope this is okay with you. Otherwise, we can also talk about it if you are having any other problems. Okay. All right. Non-removable discontinuity is when the limit does not exist. So if the limit does not exist, you can't do anything, okay? Because at the end of the day, they should exist and be equal. So the function cannot be redefined, and that is why it's called non-removable. Now, this is very, very important. First of all, go and find out the limit where it might cause trouble. If it exists, just find out why it's causing the trouble, whether fa is not defined or it's not equal, then you go ahead and remove it. But if it does not exist, you cannot do anything to make it continuous, and that's why it's called non-removable discontinuity. I hope this is okay with all of you. So what are the possible reasons why it does not exist? First thing first, it's called the finite or jump type discontinuity. It means that suppose you have all the left hand and the right hand limit, both of them exist, but they are not equal. So that is why we call them a finite or jump type discontinuity. I'll just draw a diagram so that you people understand better. So suppose this is how the function goes, okay? And then this is the left hand limit. You have seen these kind of things. And then this is how it is. Okay, so suppose this is x equals to c, and you just see that this is how it is. Okay, if you just look from the left and the right, obviously the limits are existing. So this is the limit or this is the limit, but they are finite but unequal. So as you see this jump, this gap, okay, it's called the finite type discontinuity or jump type discontinuity. I hope this is okay with all of you. Every time we are talking about a specific type of discontinuity, you also see the nomenclature, okay? Infinite type discontinuity, at least one of the limits will tend to infinity, okay? So this is again very, very important. So whenever you have the limits, it's not finite. So obviously the functional value, etc., that can't be redefined and making it a non-removable discontinuity. Okay. And another type, it's called the oscillatory type discontinuity. sometimes the limit oscillates between two finite quantities. So this is one of the types that we are going to explore. I'll talk about this one. So we'll see how these things go, okay? Once we see the examples, I hope this will be a lot clearer to you. So let's just see some examples. So let's just take the first one, okay? Tan inverse 1 by x. Now this is very, very important. If you see this, first I'm taking 0 minus, okay? So something which is less than 0. And also you take 0 plus. Okay, I want you people to see that the 0 plus limit will be pi by 2, whereas the 0 minus limit will be minus pi by 2. Okay, I'll just give you a hint. Since this is all about limits, I want you people to go ahead and figure out certain things, but at the same time, I'll just simply give you some clues, okay? This is pi by 2, all right? So what is tan inverse something? Basically, you are looking for an angle whose value tan will be actually 1 by x, where x is approaching 0. Okay, so now look at this one. This is tan x is basically sin x by cos x whenever it's approaching pi by 2. All right. So this is getting very close to 1. Sin x is getting very close to 1. And cos x is getting very close to 0, but it's obviously more than 0 since cos is positive. So this is actually going to pi by 2. I hope this is okay with you. Similarly, you will find that if it is 0 minus, then this is minus pi by 2. So obviously the limit does not exist. The right hand limit will be pi by 2, whereas the left hand limit will be minus pi by 2. And that is why it's a finite discontinuity. Is this okay with all of you, or you want me to repeat? Please let me know, because this is a little different from what we have done so far. And if you have any problems, we can always discuss. But again, at the end of the day, you understand that this is all about limits. So you have to identify the limit, and then consequently you see how the type of the discontinuity will be, because there the limiting value is causing the trouble. Okay, so if you just take the x tends to 0 plus, you will see pi by 2. For 0 minus, you will get minus pi by 2. And that is why the limits are different. They are finite, but they are different. So that is why it's a finite or jump discontinuity. Now, again, let's just take this one. This is a classic example. If you see the graph of sine 1 by x around 0, it just oscillates between minus 1 and 1. I want you people to go ahead and see the graph, okay? So suppose I'm just taking something which is very close to, suppose I'm taking this value. So this is actually 10. So you see sine 10. Again, suppose I'm taking this particular value. Okay, this will be 100, etc. So for different types of values, this will range in different quadrants. So you will sometimes you'll get some positive values and negative values, etc. And if you look at the graph, it will just oscillate between two numbers, minus 1 and 1. So this is actually oscillatory type of discontinuity. All right. Next thing. Now again, this is very, very important. Look at this one. Tan x. Okay. So suppose I'm taking pi by 2. All right. So let's just simply take pi by 2. And when it's approaching pi by 2 from left, suppose it's approaching pi by 2 from left or right, anything, just take this one. Suppose this is pi by 2. Whenever it's approaching pi by 2 from, suppose, left. Okay. So sin x is closing to 1 and this is 0. So consequently, this is actually a very, very large number. This is more of like this, 2 to the power a very large number. So this is basically infinity. I hope you understand what I'm talking about. This is pi by 2. So this angle, it's approaching pi by 2, but less than pi by 2 in this quadrant, okay? So what is tan x? Tan x is like sin x by cos x. So sin x is approaching 1 and cos x cos x is a very, very small number close to 0. So this entire thing approaches infinity. So 2 to the power infinity is, again, this is basically an infinite type of discontinuity. If you just go for this one, pi by 2 minus, you will see that this will be a very large number. So that is why this is 0. Okay. So one of the limits, if this is infinity, so this is infinite type of non-removable discontinuity. So that is why practicing this limits is very, very important. If you don't have the kind of comfort level that you should have evaluating the limits, please go ahead and revise that, okay? Because this is very important that you understand different types for different problems regarding limits. This is again very, very simple. As you see the sign of ln x at x equals to 0, we have already talked about this one. This is again oscillatory. Okay, the sign of something will oscillate between -1 to +1. So basically sign of this thing will oscillate between -1 to +1. So if I take 1/3, okay, that should oscillate between this to this. And similarly, we have 1 plus something and its box. Okay. So let's just take the box on both the sides. So what is this? This is 2/3 and this is 4/3. Is this okay with all of you? So what is this box? This box is 0 and this box is 1. So this will be actually a oscillatory type discontinuity, and this value will oscillate between 0 and 1. All right. Look at this one. This is very easy. This is something that you people should actually do, because you know that box x just causes trouble at integral points. Okay. If I just take 2 minus, this is something less than 2. So the box will be 1. This is 2. But if I take 2 plus, then this box is 2 by 2. So this is actually a finite type of discontinuity. Hope this is okay with all of you. So these are very, very important for all the cases you see the limit does not exist. Let's just take another one. See, again, this is very simple. When x approaches 1, okay, this is a very small value. So there's this numerator which is fixed, which is 1, and this is a very small value. So obviously, this is going to be approaching a very large number. So that's why this is the infinite type of discontinuity. So for all the cases we have taken here, the limit is causing some trouble, and the possible reason behind the trouble will actually give you the type of non-removable discontinuity that you're talking about. Okay. So I know this was a little different and probably difficult from what you have done so far, because it involves some very complicated ideas of limits. But if you just look at step by step, you will understand what is happening. So let's just take a couple of minutes and figure out what has been done. If you have any problems, please let me know. I'll be more than happy to repeat, because I know this is a little difficult in terms of the concepts, because you should have a strong concepts of limits, and that's why it's worth repeating. So just take a moment, and if you have any problems before I move on to the next slide, feel free to let me know in the chat box, or if it's a long query, you can also just unmute and speak. Okay, we'll take a moment and try and understand what we have done so far. So, okay, if this is okay with all of you, then you can write yes so that I can proceed. Otherwise, if you have any queries, please let me know. But I hope, repeat the last one, Obishikta. Okay. So this is like x by 1 minus x. Okay. So suppose this is at x equals to 1. So I'm taking something more than 1, okay? So this is, suppose this is like 1 and 1 point something, suppose 0, 0, 0, 0, 1, etc. And this is like this. It's just an example I've given. So as you know that this is very small, the entire value will actually approach infinity. Okay. So if this is approaching 1, this is approaching a very small number. So this is more of the type, this is approaching infinity. So that is why it's infinite. Okay. At least one of the limits will be approaching this. Okay. But again, if you take this as close to 1 but still less than 1, then this will be a very small negative number. Suppose for example 0.00001, etc. Suppose this is one of the types, okay? And whatever you have here, this is very close to 1, whatever you have. So this is a very small negative number. Okay. So this is what we are talking about. All right. So whenever you see these limits, you will understand where it's causing the trouble, whether the value is oscillating or they exist but are not equal, the left hand or right hand, or at least one of them is approaching infinity. So this is what you have. Okay. All right. Next, you have the intermediate value theorem. It's very, very simple and again, very intuitive. So let's just see how this goes. We have taken a continuous function on a closed interval where the extremities are not having the same functional value. Okay, f a and fb are different. Then if you take any value between fa and fb, you will at least have one x naught in this particular interval where the functional value is c. So if it looks pretty complicated, we'll just see a very simple example. All right, I have taken this interval a to b. Okay, this is the graph. So what is fa? This is fa and this is fb. All right, I have taken any value c between that. Okay, so I have taken this fa and fb, and you take any value c between that, obviously you will have a point where the functional value is c. I hope you understand what it means. And now let's just concentrate on this part, at least one value. Look at this part. I have taken fa and fb here. So this is fa and fb. Between that, we have taken c. Take any point. So you will actually see at least one x naught. Here we have taken x1, x2, x3. But at least one point will be there for it to be having that functional value. I hope this is okay with all of you. Still, if you have any doubts, please let me know, because this is very, very intuitive. Okay, so there's a continuous function having different values at the extremities. So between those two values, it take any value, at least it will be one of the functional values, okay, in that interval. So I'll do one example with you so that you people understand it better. If you still have any queries, we'll just come back and answer, okay? Let's apply and see one possible, application of this. You have to show that this particular equation has a solution in this interval. Now, this is a very good sum. Whenever you have all these, these kind of sums, you try and solve these and see whether one of the roots are in this interval, etc. But sometimes solving these kind of equations are not very easy, okay? So that is why here we are using a different method. So let's just see what we can do here, okay? See, suppose this is fx. As you see that it's a polynomial function, so it is obviously continuous, and consequently it's continuous on this interval that we have taken. Now what do we do? This is our first part, taking this continuous function. Now what we do is we take the extremities, okay? So 0 and 1. All right, I hope this is okay with all of you. So at 0, the functional value is 1, and at 1, the functional value is -1. Okay, so what are the possible numbers? These are the possible numbers, 1 and -1. So if I take any value between 1 and -1, that should be a possible functional value. Now, this is very, very important. For the solution, what do I need for the solution? I need fx equals to 0, which is definitely in this -1 to 1 range. So obviously, I will get an x naught in the original domain that we have considered, which is 0, 1, such that this will be true. All right. So obviously, it has a solution. Is this okay with all of you? This is a little different, approach to what we have done so far. This is very interesting, a good approach to show whether a particular equation is having solution in an interval or not. So this is one of the things that I wanted you people to see, how we can differently apply this particular theorem. So this is very important again. So let's just see one very intuitive thing. As I told you people that this intermediate value theorem is very intuitive. So suppose you're climbing a mountain and this is the base position and this is where you want to be. Just assuming the path is continuous, you will actually reach the intermediate position at least at one time of interval. So this is very intuitive. So that's what we have used for intermediate value theorem. Very simple and intuitive theorem, but also with a lot of applications. You have already seen one application of finding out the roots in a particular interval. So whenever sometimes you see all of a sudden, in an MCQ exam or any entrance exam, you just see these kind of questions, just check in which interval it can possibly have a root. So this is one application of the intermediate value theorem. All right. So still, if you have any doubts in this one, please let me know in the chat box. And I think we'll just move on. Now, this is very simple. We have already talked about algebra of continuity. Here we are going to talk about continuity of composition of functions. Okay, very simple. We have taken two real functions such that f composed g is defined. Now, this is very important because at the end of the day, no matter what we are talking about, it's composition of functions. Okay, so whatever is required for that composition to be defined, that is our basic requirement. Okay, so g is getting operated first, so it's actually continuous at x equals to a and x equals to ga. At this point, f is continuous. So I hope you understand. After g is done, then this f will operate. That's why. So these are the reasons. So the composition of the continuous functions will be actually continuous at x equals to a. So this is another result that we are doing for continuity. Simple. So let's just take one example. If you look at them individually, this is something we have already done. And this is a modulus function which is continuous everywhere. So obviously this is going to be continuous. See, what we have taken here is the composition. Okay. So suppose I just give you one thing. E to the power sin x, mod of that. Very simple. So e to the power something is e to the power x is always continuous. This is continuous. Then you take the modulus. All of these are continuous. So if you have these kind of complicated functions, again, look step by step. Okay. Whenever you have this compositions going on, look at the parts individually. If they're continuous, then the composition will be continuous. All right. I hope this is okay with all of you. But still, if you have any doubts, let me know. So that's it from continuity. We'll just simply move on to differentiability now and explore this as well. Okay. In the meantime, if you have any problems, please let me know. If there's any problem, please let me know. Now we are starting with differentiability at a point. All right. Okay. Take any real function and any point. Now, this is something I want you people to see. First of all, you're already familiar with the very basic first principle of differentiation. Okay, so this is what you originally had in the first principle. This is what you had in the first principle. But just like the normal cases where things are like, okay, terms and conditions applied, you probably didn't notice one part. F dash x equals to f limit h tends to 0 f x plus h minus fx by h. All these things were there, comma, provided the limit exists. So back then we didn't actually care about them, because all we discussed about was some very standard functions. You have already seen how we differentiate sin x, cos x, e to the power x, etc., which do not cause any trouble. But there can be functions where this limit does not exist. So for differentiability, if this is something that you're already familiar with from the first principle, but this is very important that you understand the limit exists finitely. Okay, so two things. What about the existence? Simple existence of a limit tells you that the left hand and the right hand limit should be equal. Very simple definition, very intuitive thing that we have. Shomojyoti, do you have any queries? You've raised your hand. So let me know in the chat box if you have any queries. So this existence of limit is something that we are all very familiar with. Whenever this limit will exist, obviously the left hand and right hand limit should be equal. All right. So how do I actually represent this left hand limit? F dash a minus. Okay, since we are talking about derivative, this is actually the left hand derivative and this is the right hand derivative. So for left, this is a minus and this is a plus. So I hope you understand what we mean by the left hand and the right hand derivative, and it should exist. Okay, and what do you mean by finitely? Obviously the value of the limit should be finite. This value is known as the derivative or the differential coefficient of the function at x equals to a. And as you know, it's denoted by f dash a or any other possible notation that we use. So this is the final result that you are all familiar with, but we never looked at this particular part. Okay, so this existence and the finite value, this is very, very important. And as you know, for existence, this left hand and right hand limit should be equal. I hope this is okay. So we'll do some more examples and see some theory, so things will be better. So simple thing, fx equals to x square is differentiable at x equals to 1. This is what you need to show, and you have to find f dash equals to 1. Now this is very simple, as in how to different x square, etc., using the first principle or maybe the direct formula, all these things. So we have to see whether this is differentiable. So what we have done is we have taken the left hand derivative. What is the left hand derivative? Whatever limit that you already knew, the same limit from left hand side. So I hope this is okay with you. So whatever you have already known in terms of x, f of x plus h minus fx, etc. So this is what you have. Okay, so I guess this is okay with all of you. Okay, now what you do is you just simply put the value and evaluate the limits. Fair enough. Similarly, right hand limit, very simple. So as you see, all these things, they involve a lot of concepts and minute details of limits. So again, I'm telling you for the nth time today, go ahead and revise it, and that's why it's very, very important. So as you see, the left hand and this should be plus 1, and the right hand limits, they are equal. So consequently, what you see is basically it's actually differentiable at the particular point that we have considered. So as you see, this commonly shared value, this is nothing but f dash 1 that we are looking forward to. Okay, so whatever we knew from the first principle or the normal straight away formulas that you're already familiar with, this is what you have here. So yeah, that's it. Okay. So this is what we have taken. We have to comment on the differentiability of this function at x equals to 1. All right. Okay. First of all, the left-hand derivative. You already know up to this portion, this is very, very simple. But now look at this, okay? This is something a little less than 1, all right? So you know for less than 1 what formula you're supposed to use, what part of the function you're supposed to use. That this is fx equals to x, so this is just coming out as 1 by h, all right? And this is minus h, etc. So it's very simple. Similarly, this is the right-hand limit, the right-hand derivative, which is actually the right-hand limit of the original limit that we have suggested. The first two steps are pretty simple because they are literally everywhere. Now, if you look at this 1 plus h, okay? So this is more than 1, so which is the format that you're going to use? This is actually x squared, okay? So this is what you have. Some very simple manipulations, and this is what you get. I hope this is okay with all of you. So as you can see, this is 1 and this is 2. So obviously they are not equal. Consequently, it's not differentiable at x equals to 1. So this is very, very important that you understand this properly, that, you know, whenever there's this left-hand limit or the right-hand limit, you see how it goes. All right? Is this okay with all of you? If you have any doubts, please let me know. All right? It's very simple. I really don't know what's on that screen because obviously, is there any one of you who have used some ink on the slides that you people can point out? I don't know. I thought that since I'm presenting, I'm the only one who can see this. Okay. I hope this is clear. Yeah. I hope this is visible now. I don't know what happened all of a sudden. I didn't use that ink. But anyway, so let's just see one thing. Okay. This is the left-hand derivative. And this is the right-hand derivative. Fair enough? So the left-hand derivative is 1 and the right-hand derivative is 2. Obviously, they're not equal. But let's just look at one thing very quickly. Okay. So if you look at this x, which is less than 1, for less than 1, what is the differentiation? The differentiation is 1. And for this one, the differentiation is 2x. By the way, who's using this board? I really don't know. I mean, I don't know how to restrict that. Okay. Just wait a minute. What's going on? Just a moment. You know, whatever you people have used, any ink or something, I don't know. Since I've already taken the, seen this problem, I thought this is only visible to me as something is going on. Just a moment. Shagnik, as you suggested, is there, I don't know who's doing this. This is not, it's not right. Some of you who have done this one, please, yeah, if you have done this, if you have done this by mistake, then please just erase this one. Just use the eraser option and erase the ink on the slides. Great. If you've done this by mistake or anything, please erase the ink on the slide. Something I really don't know what's going on. Shagnik, as you suggested, you know how to restrict the use. I'm not really familiar with this. Anyway, let's just look at this one. This is 1, okay? And if you differentiate it, you are getting 2x, all right? So what is at x equals to 1? This derivative will be 2. So as you see, the left hand and the right hand derivative, they're not equal. Consequently, it's not differentiable at x equals to 1. I hope this is okay with all of you. So that's it. If you still have any problems, we'll just take a moment and clarify any doubts you people have. All right. I really don't know how to change the settings, at least for today. At least whoever, I really don't know. This is absolutely horrible. I don't know who are writing these things down. Please just remove the ink. You can always use the chat box. This is causing some sort of problem in the entire lecture. This is not fair at all. Okay, I'll just ask Maniji next day so that he could control whatever is being written here. So yeah. All right. I hope the previous one was okay. Now, since we know the basics of continuity as well as differentiability, we are going to talk about their relations and how we can actually, relate them together, and whether the existence of one should guarantee the existence of the other, etc. The first thing we normally do is, if a function is differentiable at a point, it is necessarily continuous at that point. Uh, I think just we'll take a break for 5 minutes. I'll talk to sir and see what we can do, okay? Just take a break for 5 minutes, everyone. We'll just take a break for 5 minutes and just be back by, 11:05, around that, a little more than 5 minutes. Let's just take a break, and I think just I'll see how we can sort this one out, okay? Let's take a break and be just back by 5 to 7 minutes. All right. So are you guys back from your break? Just write yes so that I can start right away. Should I start? All right, are you people here so that we can start? So we have already done up to this portion. All right. So something we were talking about. So should we start then? Just write yes so that I know you people are here and we can start with the class. You can just come back. All right. So this is the standard result that we are going to see. Okay. If a function is differentiable at a point, it is necessarily continuous at that point. So this is one result that we are going to use literally everywhere. So if you prove differentiability, that is enough. You don't have to worry about continuity individually. All right. So the obvious question, this is something that I keep on asking you whenever there's any result that we have considered. If differentiability is implying continuity, is the converse true? So what we do here is we can actually check this with a counter example. The converse is not necessarily true. This is something I want you people to go and figure out. If you take this fx, okay, as mod x, this is continuous at x equals to 0, but this is not differentiable, all right? So just one thing I want you people to see. If you just take this one, this is going to be continuous, okay? But if you differentiate it, you will see that this is not differentiable, as in the left hand and the right hand differentiation should not be equal. If you take the left hand differentiation, just try this one out on your own. The left hand differentiation and the right hand differentiation will be different. So differentiability implies continuity, but the converse is not true. So if a function is continuous, it's not necessary that it is differentiable. Okay. So this is the basic first principle that you know. So what does it represent? It actually represents the instantaneous rate of change or slope of the graph. You already know where this f dash x comes from, this dy dx, etc. What is a small change in x or small change in y corresponding? All these things, this actually geometrically or kind of, this is a significance of f dash x. It just represents the instantaneous rate of change or slope of the graph. Okay, so when do you think the derivative may be undefined? Okay, when there is this slope which is not defined. Okay, so if you take any vertical line, you see the slope is not defined. And also if there's a cusp or sharp edge or jump or hole, or there's any unmeasurable slope, those are the points where derivability can be under the scanner. For example, since we were talking about mod x, let's just see how this graph goes. Okay, for x less than 0, 0, and x, can you see this sharp bend here? This is where the differentiability is having some trouble. Let's just see another graph, just simple graph. Okay, where do you see some sharp bendings? These 2 points. Okay, so these are the possible points, okay, where there's a sharp edge or a jump or some gap, or suppose there are certain other portions where this can be undefined. I hope this is okay with all of you. We'll do some examples. Okay, and since for differentiability there should be this instantaneous rate or the slope or measurable rate or slope which should be defined. So whenever you take differentiable functions, it must be continuous. Okay, it must be continuous. But again, I have told you that we can have certain functions which are not differentiable, though they are continuous. I hope this is okay with all of you. Otherwise, if you have any problems, please let me know. Let's just see some more examples so that we have some clarity. If you have your if you have your audio on, please mute your audios so that other people can talk. I really don't know what's wrong with you people. If you don't want to attend the class, you can go ahead and all right. So this is the first thing that we have done here. As you see, there's no point, there's no problem with the continuity. But as you see at this x equals to a, there's this change in the behavioral pattern of the function. Sometimes, we talk about a cast where it's changing its behavioral pattern, etc. So these are the points where the differentiability is questioned. Okay. Similarly, if I take this one, as you see, this is continuous as well as differentiable. There's no point, there's no cast or jump or age or sharp bending, etc. So this is perfectly all right. So another example, now this is very important. As you see this particular slope, this tangent, this is actually not having a measurable slope, okay? So if you look at this particular line, this is actually parallel to the y-axis. So of the form x equals to c. So the slope is kind of undefined. So that is why this is the possible point for problems with differentiability. I hope you understand this. If you have any problems, please let me know. So I wanted you people to get some idea from the graph as well, because you know how to check the differentiability in the normal way. You just go for the left hand derivative or the right hand derivative, etc. So otherwise, these are the possible things. Shomojati, if you see this particular point around this, it just changes its behavior. As we were talking about cast or some sharp bending, etc. And those points, the slope of the graph, the instantaneous rate of change, that is not defined. And that is why the derivative does not exist at x equals to a. Okay. So I hope this is okay with you. Just the way, if you just take one very classic example, if you see this mod x, this is where it bends sharply. So this is the point of discussion when it comes to differentiability. Is this okay with you? Okay. Let's just do some application. So as you see, this is pretty complicated looking function. There's the first part of the function which is defined between 0 to 2, and the second part is defined between 2 to 4, and you have to comment on the continuity and differentiability of fx at the given points. Okay, so first of all, we are starting with continuity at x equals to 1. Very, very simple. You know how to do the continuity thing, that the left hand limit, right hand limit, and functional value. Fair enough. So this is what we have taken. All right, so what is this? This is a signum function, okay? So if you remember, this is a signum function of box x. Now this is very, very important. If you have any doubts, please let me know. 1 plus. So something is more than 1. So the box of that will be 1. And signum function, you know, this is 1 when x is greater than 0. The signum function is minus 1 when x is less than 0. And 0 when x is equals to 0. All right. So this is what you have. So since box x is actually 1, which classifies in this portion, so this part is 1 and this x square is 1. So that's why you have this 1. And what is the fractional part of x? This is very simple. This is x minus box x. Now, what is box x? Box x is 1 and x is very close to 1. So this is 0. So I hope this is okay with all of you. I hope this is calculation is okay with all of you. Still, if you have any doubts, please let me know. Similarly, we'll just go for the left hand limit. Now this is very important. Something is less than 1. So this is 1. So it's approaching 1 from the left. So this is less than 1. So what is box x? Box x is 0. So what is signum function? This will be actually 0. Okay. So I hope you understand. So what is this? This is actually x minus box x. Now box x is 0. So you will simply get 1. Is this okay with all of you? Just see the calculations. And also this is the functional value at x equals to 1. Okay. So these are the things that we have taken into consideration. If there is any problem evaluating this limit, please let me know. It's not very difficult. Just break it up into pieces, examine how things will be, and the rest is pretty simple. All right. So this is continuous at x equals to 1 because the left hand limit and the right hand limit, it's equal to the functional value, which is perfectly all right. Okay. Now, what do we want? We want the differentiability. This is what the differentiability will be like for right hand derivative. Okay. This is the right hand derivative that we have taken. Very simple formula. All these things actually belong to this particular portion where x is between 0 to 2. So that is what we have used. Now what is box 1 plus h? That is 1. So signum of that function is obviously 1. So you know what this is? This will be actually h. Okay. So this is the original input and the box is obviously 1. So the fractional part is actually giving you h and this minus 1 is as it was. Okay. Simple calculations. So this the right hand derivative is 3. So the calculation is not very difficult. Just go step by step. Try and understand how this box function will be, how the signum function and the fractional part function. Okay, so whenever we were kind of repeating the continuous basics, some functions in the lecture, the second lecture. So I hope you understand why it's very, very important to brush up the ideas on certain standard functions and limits, etc. Okay. This is another thing. Again, very simple. Similarly, what is this? This is actually going to be 0 because I've told you that this box 1 minus h is 0. So the signum part will be 0. And for this one, you have all the other things sorted. It will come out as it was. Okay. So the rest of the things are pretty simple. So you will get 1. This is the fractional part. This is less than 1. Okay, this is 1. So this is something less than 1. So its box is 0. So the entire output is the same. And obviously you have minus 1 and divided by minus h. So the limit is 1. Problem, it's not differentiable at x equals to 1. Okay. So this is very, very important. At x equals to 1, we have seen that the function is continuous but not differentiable. And this also assures you that if a function is continuous at a certain point, there is no assurance that it's going to be differentiable. So I hope the continuity and differentiability at x equals to 1 is clear. Now we are going to go ahead and see how the x equals to 2 thing will look like. Okay. Now this is very important. Around 2, this will change its behavior. So you have to take the definition of the function accordingly. All right. So this is the first thing that we are doing. X tends to 2 minus fx. This is what we do. Simply just put the value for less than 2. The first part of the function is being used and we evaluate the limit. Okay. And this is what we have as the right hand limit. So it cannot be equal because at the end of the, even if you don't know what sine 2 can be, okay, even if you don't know don't know the exact value, it doesn't matter. Anyway, it's going to lie between -1 to 1. It can never reach 5. So it's not continuous at all. So consequently, this is not differentiable. This part is very, very important. Because, if differentiability implies continuity, so if this is not differentiable, continuous, it cannot be differentiable. Okay, is this okay with all of you? Just one thing, I'm just saying that differentiability implies continuity. Okay, so what is the equivalent of this? Negation of continuity implies negation of differentiability. So if this is not continuous, this cannot be differentiable, because if it were differentiable, it would have been continuous. So checking continuity is enough. If it's not continuous, obviously there's no point checking its differentiability, because it won't be differentiable. Is this okay with all of you? If you have any problems, feel free to let me know. But at the end of the day, there's a lot of importance on calculating the limits. So make sure you do these things properly. If you have any trouble regarding that, revise and just practice more so that you can become better. Okay. This is something that I'm going to go quickly through, because you're very, very familiar with these things. AB, at every point of AB, just like continuity, there's nothing new that we have to do here. Very simple. Just like continuity, we have a very similar approach to differentiability, very intuitive. So this is what you have for every point. The left hand and the right hand derivative is equal. For the closed interval, what do you have? Apart from the corresponding open interval, you also have the extremities, all right? For A, you have the right differentiability. For B, you have the left differentiability. It's very, very similar to the approach in continuity that you're already familiar with, okay? Half open, half closed, again, very similar. So the open interval is literally there everywhere. Otherwise, if you have any extremities included, make sure you consider that point. And depending on which extremity is there, you're taking the right hand or left hand. Since A is included here, obviously this right hand derivative will be under consideration. If I include B, there will be the left hand derivative under consideration. Very, very simple and intuitive, and very something very similar to the continuous things. Okay, so I'm not going into the details. I hope this is okay with all of you. We'll just do some examples. Before that, obvious things, just like continuity, if it's actually differentiable at each and every point of its domain. Now this is very important. So what is the difference? Here we have taken the domain. Here it's the entire real number line. Okay, so this is everywhere, and this is just simply generally differentiable functions. Okay, all right. Some special differentiable functions, just like we talked about some special continuous functions like the polynomial, rational, modulus, constant, or trigonometric, logarithmic, etc. So there are certain special functions which are differentiable too, like the polynomial, trigonometric functions, exponential, logarithmic, inverse trigonometric, all these things that you're familiar with. These are some really special differentiable functions that you already know. Okay, just like continuity. But the only thing is, whenever you're just saying this everywhere or in their respective domains, so that is the only difference. Okay, sometimes the entire domain is a real number, so it's differentiable everywhere. Otherwise, they are obviously differentiable in their respective domains. Okay, very simple. So this is what you have. So this is how you are redefining the entire thing. Nothing special though. Identity function, which is a polynomial, obviously it's differentiable. This is again a polynomial function. This is differentiable. So this is the one at question. Okay. So I have actually done this exact similar sum before. You have questioned the differentiability of this function at x equals to 1. So this is how you generally extend the idea of differentiability at a point to an interval. And whenever you consider the entire interval, if you know some standard differentiable functions, things will be a lot easier. Okay. We have already done this, so I'm not repeating this. So obviously, if you take this one, if you just differentiate this, you have 1, and for this one you have 2x, which will give you 2. So very easy and simple approach. Otherwise you always have the basic limit going on. So it's literally differentiable everywhere except for at x equals to 1. Okay. So whatever we knew in terms of the points, what we are doing here is just extending the entire thing into intervals. Okay. Again, very, very simple. Something that you already know, something that we have already discussed about. Just like continuity, we have taken the differentiability, the algebra of differentiability. So as you know, f and g, they are differentiable functions at a particular point. Then their sum, their difference, their product, their quotient, and also the scalar multiplier, etc. All these things will be differentiable at the point. Okay. But just for the quotient, be sure that the denominator, that polynomial or whatever function you have, okay, make sure it's non-zero. And if it's 0, just don't take this into account. Okay. Whenever you take the common domain, just make sure you eliminate the points where it can be possibly 0. All right. Very similar to continuity. But what I want you people to understand is some good counter examples. As I said that fx and gx are differentiable, so their product will be differentiable, etc. The converse may not be true. In the, we have around 3-4 slides here, and then we'll just complete the theory part. I'll show you some examples of converse things. Okay. Here I'm taking a differentiable function and another non-differentiable function and show you the product can still be differentiable at x equals to a. Okay, so this is mostly the converse thing. So these are the two possible functions I have got, x and mod x. This is differentiable at x equals to 0. This is a classic example. We use it literally everywhere in differentiability. Not differentiable, I'm taking the product. Okay. So product is very, very simple. You know how mod x behaves. So if you take the product, you will see that this is differentiable everywhere, including x equals to 0. Again, a very, very simple approach. This is 2x and this is minus 2x, okay? So when you are taking x equals to 0, the left hand and the right hand, both the derivatives are 0. So this is actually differentiable at x equals to 0, though individually they are not differentiable. So this is what we are trying to do here. Just understand, apart from the algebra of differentiable functions, the converse may not be true. We might have different types of things which are probably not both of them are differentiable, but their product is differentiable. Okay. All right. So let's just take another example, very simple example. Again, two functions, none of them are differentiable, but you take this, you take the product, this is perfectly all right. You know that this is a polynomial, so this is perfectly all right. So I'm just showing you some counter examples where it's not necessary that if a product of two functions, it's differentiable at x equals to a, it's not necessary that both of them have to be differentiable at x equals to a. Okay. So these are the things I want you people to see. So let's take another example. We have already said that if fx and gx are both differentiable, then f plus g that is also differentiable. Okay, but here I'm taking you actually giving you an example where they're not differentiable but their sum is differentiable. Simple. I've taken mod x, have some problem at x equals to 0. Similarly, this minus mod x, how this thing will look like. So suppose this is actually, mod x. Okay. So you'll also have this minus mod x thing going on. Again, you'll see that this is the problematic point. So none of them are differentiable at x equals to 0. But this is very simple. This is a constant function, so obviously it's differentiable everywhere. So I hope you understand what we are talking about. So I've given you some good counter examples from where you can understand that though these algebra of differentiable functions are definitely applicable, the converse may not be true. All right. Let's do some examples. Just one example. This is what you have, and this is how the graph will look like. Again, it's a very sharp bending. If you take the right hand derivative, the derivative will come out as 2, whereas the left hand derivative is 0. So obviously this is the point where this is not differentiable. Okay. So I hope this is okay with all of you. So we have explored different types of counter examples here. So whenever you apply these algebra of differentiation, make sure you understand and apply it properly. Sometimes the converse may not be true. So be a little careful about it, okay? The last thing, similarly, that you have done for continuity, quite similar to that, the differentiability of composition of functions, very similar. If I take two functions, the first one is differentiable at x equals to a, and the second one is differentiable at x equals to ga. So their composition will be differentiable, okay? But again, whenever we talk about any result, it's very important to check the converse, whether it's true or if it's not true, just, go ahead and check some counter examples. So this is what you have, okay? The converse may not be true. So the obvious question is, let's just see some counter examples. This is what you have. Suppose I have taken fx equals to x square. All right. So for fx equals to x square, what you have here, you have another function gx equals to mod x. This is the composition. This is nothing but x square. So first of all, you take this mod x, then you take whole square. So this is x square, which is differentiable, but this is differentiable, though this is not differentiable. Okay, so the converse is not true whenever you are taking the differentiability of composition of functions. Even if you take a couple of functions, suppose one of them is non-differentiable, still it might happen the composition is differentiable. So I hope this is okay with all of you. That's what we have from the theory part. So if you have any problems, please let me know, because now we are going to start with the class exercise, okay? So if you have any problems up to this portion, let me know, so that we can move on to the class exercise. And if this is okay up to this portion, I want you people to just respond in the chat box if you have any problems, or if this is clear to you, then just write yes, so that we can move on to the class exercise. Otherwise, for any queries, feel free to ask. Okay, all right. So, is there anything that you want me to repeat? And also, when we are going to do the class exercises, you'll see a lot of, similar approach and a lot of concepts getting revised. So, yeah, you can always talk about that later. Okay. So, very simple class exercises we have, but we'll try and explore different types of things, so that the entire chapter is covered properly. And in the meantime, whatever concepts you're using, if you have any problem regarding that, please let me know. Now we have to determine the continuity of this particular function at x equals to 0. This is something that I have already done with you people. This sine 1 by x has an oscillatory discontinuity at x equals to 0. But as you see, we have this accompanied by x square here. Now, this will be very interesting to see how this changes the entire course of continuity. So, this is the left-hand limit at x equals to 0. So, it's very simple thing that we have put here up to this portion. Now x square, when x approaches 0, x square will also approach 0. Along with that, I have a finite quantity that oscillates between -1 and 1. Now this is very interesting. You know that anything that's multiplied by 0 will give you 0 provided, okay? Yeah, Shomajyoti, if you want to use any other properties, you can use that as well. But whenever you are using different limits, make sure the standard form that you are using, it's kept properly. Okay, because suppose you are using something for sine x by x, etc. You should know where the limit should go, like x tends to 0, etc. So this is something you know, you should be a little aware of. Otherwise, you can use any other properties. So 0 into anything finite, that will give us 0. And similarly for the right hand limit, it's a simple thing. And obviously the functional value is 0 because this is already defined as 0 when x equals to 0. So this is perfectly all right. So this is one example, very simple example I wanted you people to see. So when sine 1 by x was alone, it was oscillating. There was this oscillating discontinuity because it oscillates between -1 and 1. But here, since you have these things accompanied by x square, so when x is approaching 0, x square is approaching 0, and it's getting multiplied by a finite number. So the ultimate answer is 0. It doesn't really matter what is there. At the end of the day, it's a finite quantity, so the entire result will be 0. So this is a very interesting example that you should check out because we have already done sine 1 by x, which was not continuous. Okay. Now, this is something I want you people to figure out. It's very, very simple and bad. So just tell me the value of k. It should be continuous. This is something that you people should do. It's very easy. For continuity, you know the left hand and the right hand limit should be same, and also the functional value. Okay, just try and find out the value of k so that it becomes continuous. Let's try this one out. It's not very difficult. For the left hand limit and the functional value, we use this one. For the right hand limit, it's very simple. It's a simple substitution. The limit is not very difficult as well. Try and find out the value of k, okay, such that it becomes continuous. Okay, I've already got one answer. So you just try this one out. It's very, very simple. It's not difficult at all. And even the limits from what you have done already compared to that, this is absolutely easy. There's nothing difficult at all. So I think I've already got one answer. To see some more answers. Try this one out. There's no way you should miss out on this one. It's very easy. And the limit is like simple substitution. There's nothing to do in terms of the adjustments or standard results, anything. Okay, so people are saying it's -2. So let's just see. It's absolutely simple. So this is what you have for less than 2. You're using the first part. And now this is the simplest thing that you can get. Whenever you have this particular limit going on, just put the value and that's it. Similarly, these are the possible values and this is the functional value. For continuity, they should be equal. So from there, you can clearly get the value of k. It's perfectly right. This is k equals to -2. Good. It's very simple. You just find out the left-hand limit and the right-hand limit. Since they should be equal, this should give you the value of k. All right? Chalo, the next one. You have to judge its continuity at x equals to 1, which is very simple because, you know, if you look at the original function, it changes its behavior around 1. So you have to see the left-hand limit and the right-hand limit as well as the functional value. This is the functional value, which is very simple. You just put x equals to 1. Look where the equality is. This is box 1, which is 1. Left-hand limit. So this is the part of the function that we have considered for left-hand limit. This is simple. If I just put the value, these are the easiest type of limits, simple substitution. Again, right-hand limit, you're using this part of the function. So box 1, something more than 1 actually. So it's perfectly all right. So it's continuous, okay? So you know these things are pretty simple, but whenever this function defined, you know, differently in a part of the domain and differently in another part of the domain, make sure you take into account which part of the domain you're talking about. So if it's less than 1, we have used the first part, whereas for greater than or equals to 1, which is for the functional value. So this is something that you need to be a little cautious about. Otherwise, these limits are very simple, like way simpler compared to what you have done in Signum function, box functions, and all those things. Now, this is this is a very good question in terms of the fact that we are also going to use some things about limits here apart from the derivability, etc. So you need the right hand derivative as well as the left hand derivative. Okay, so first of all, let's just go ahead and find out how the right hand and the left hand derivative will be. That will give us some relations between A and B from where we are going to find out their values. Okay, so this is what you have. Fair enough. Just put the value of f1 plus h, and what are you going to use there? This part, because this is what happens for x greater than or equals to 1. All right. I hope this is okay with all of you. So whenever we have taken 1 plus h, so this is the part we have used. And similarly for f1, since this is having this equality portion, this is what you have. Okay. Simple calculations, this is getting cancelled and this is what you are left with. So this is again simply 3a. So this is the right hand derivative. Very simple right hand derivative. Now you go ahead and find out the left hand derivative. All right. So very similar, but whenever I am taking this 1 minus h here, make sure you're using this particular part of the definition of function, okay? Now, these things are very important so that you understand which part you're supposed to use. So this is what we have taken, a plus b x squared. Now, for f1, you know how things should be, okay? This is the second part, which is this one. All right? So this is what you have. Now, look at this. There's one thing that we are going to use where we will have a relation between A and B. This is very, very crucial. As you see that, if I take this part, okay, this H will be there in the denominator. If I take this part with H individually, this will get cancelled. cancel. So you'll basically have minus BH, which is 0 when H is approaching 0. Similarly for this one, etc. So look at this part, okay? If H is approaching 0, this is going to be something in general undefined, the exact value. So it's getting either to a very big positive number or negative number, etc. So for definition, so for this to be defined, this should be 0. All right. Otherwise, this would have been something by minus H, where H is tending to 0, etc. So this would have been undefined. So this is what we have. From there, we have a relation between A and B. Okay. So if I go back and put this as 0, you will see the right hand limit. I'll just go back, okay, so that you people can see. If this part is done, if this is not there, so obviously you have this as minus BH, okay, plus 2B. I hope this is okay because this part is gone. Now if you put H, this is going to go and you just have 2B, all right? So this is what you have here. So 2B is nothing but 2 into A plus 1 because B is A plus 1. Now this is the left hand derivative. The right hand derivative was 3A. So this is what you have for derivability at this particular point. Consequently, you can find out the value of A and B. Okay. Sorry. So if this is okay with you, then if you have any problems, let me know. Apart from the fact that for differentiability, you should have left hand and the right hand limit equal, then the limit should be finite as well, okay? So this is one condition, one general condition that we have taken from the concept of limits, okay? This is very crucial because this is from differentiability and this is solely based on your idea on limits. So let's just move on to the next example then. Okay. Very simple, and we have to find it out, and we'll just use the fact that this is something we have been provided with, all right? So let's just see the one we have to evaluate. So I'm giving you a very simple manipulation. What we have done here is, suppose I'm taking this minus FA, okay, and plus FA, and then just separate things out with algebra of limits. Very simple. I hope this is okay with all of you. So this is the first thing we have done. Now see, this is kind of looking like this f dash a, etc. But this is 2h. This is minus 3h, okay? So what we do is, we just adjust, okay? So for this 2h, I need 2h here, or I need minus 3h here. So this is what we have done. But whenever you're taking these constants, they should be adjusted properly, all right? So since we have taken 2 here, this 2 has been adjusted in this portion, and also this minus 3 has been adjusted here, which makes it plus 3. I hope this is okay with all of you. Now, if you look at this particular, let's look at this one. Limit something tending to 0, f of a plus that thing minus fa divided by that thing, okay? So now you can clearly see how the standard form looks like. Similarly here, I have also written this so that you have a better understanding of what's going on. A plus, this is the one that we have added. This is in the denominator, and this is also tending to 0. So this is actually f dash a. This is also f dash a. So this is the result, okay? So we have used the basic standard first principle for f dash a, but instead of the exact limit that h tends to 0 or whatever, we have used the general pattern. So a plus h, our denominator is also h is tending to 0. We have maintained the pattern so that we can use f dash a. I hope this is okay with all of you. So we'll move on to the next exercise. Okay. Still, if you have any doubts, you can let me know. All right. As you look at the function, looks horrible. And look at the first part of the question. Find the points at which the continuity and differentiability should be checked. Okay, so whenever we talk about continuity and differentiability and you have this complex function going on, what we normally need to do is just some basic observation about the function that it's consisting of. All right, so let's just see at which point you should check these things. First of all, look at this portion and also this box of something. Where do they cause a trouble? At integral points, right? So box 2x, when is 2x? So if x is between 1 to 2, then 2x will be between 2 to 4. So what are the possible points where it can cause trouble? When 2x is 2, 3 or 4. So consequently, x is 1, 3 by 2 or 2. I hope this is okay with all of you. So I've just taken the first part, which is box 2x, and explored the fact that where this box is causing me some trouble, that's the integer. So consequently, when will be 2x integer? When x equals to 1 or 3 by 2 or 2. Also take care of this range, okay? Next, just look at this Signum function. You know that the Signum function changes its behavior at x equals to 0. So that is the problematic point. When does this become 0? That is our question. This becomes 0 when it's 4 by 3. So obviously 4 by 3 lies in this range. So this is another point that you should consider. So we are done with the first part then. We have taken this one and got the first 3, and for this one you are getting 4 by 3. All right. Now look at this one. This is the fractional part function. What is the fractional part function? That is actually x minus box x. Okay. So you know that we don't have any problem with x because it's a identity function, but box x can be problematic at integral values. Okay. So when do we have this as an integral value? This is very important. It happens when x equals to 2 by 3. Okay, so if x equals to 2 by 3, this becomes 1. So obviously, which is an integer. So this is going to cause the trouble. So 2 by 3 is corresponding to this part. All right. So the last part that we are going to consider is this. Box of something. Again, integral values. So look at this. If I put 0, this is actually sign 0, which is 0. So which is an integer, that is problematic. Again, what is the next possible thing that we can do here? Suppose I'm putting x equals to half. Then you get sine pi by 2, whose value is 1. Again, box 1, that will be problematic. Similarly, if I put x equals to 1, that is also giving me sine pi, which is 0. Again, that's an integer. So the possible problems are literally here. But I'm not including 1 because if you see this, this is not included, okay? So these are the two possible problems. So these things are very, very important. So just look at the function, look at the, breakups one by one and see where they can possibly cause us some trouble. Okay, so you will understand which are the possible points where you are supposed to check the continuity and the differentiability. Okay. So I hope up to this point it's okay. And we have to comment on the derivability at x equals to 1. So what I'm going to do is I'm simply, Shomojati, what is 2 by, okay. Look at this one, okay. If I just see, this is 2 by 3 is actually corresponding to this particular part. What is this? This is a fractional part, okay. What is the fractional part? Fractional part of x is actually x minus box x. All right. So where does it cause trouble? When this is actually an integer. If I take this one, When does it become an integer? From this particular range, if I put x equals to 2 by 3. I hope this is okay now. You understand, when I put x equals to 2 by 3, it just becomes fractional part of 1, which is a little problematic because this is an integral point and it changes its behavior, okay? So so 1 is not included, that is what I'm saying. Look at the value. Look at the value of x. This is the value of x. This is definitely included. The final value doesn't matter. X plus 1/3 doesn't matter. The value of x matters. So which is 2 by 3, which is definitely within the range, okay? Okay. So I hope if you look at the parts of the functions individually, you will understand where this comes from, all right? So since we are supposed to check the derivability, the easiest thing is to check the continuity. So if it's not continuous, obviously it won't be derivable. Now we are checking the continuity at x equals to 1. So as you see, this is one problematic part because it's changing its behavior around x equals to 1. So let's just go ahead and check the continuity there. So very simple, not so simple though anyway. So just be patient with the calculation, something less than 1. So this part is used, okay? So this is what you have. If I just simply put x equals to 1, this is sine pi, okay? Sine pi is nothing but 0. So obviously this is 0. I don't even care about this particular portion. This is 0. Anyway, it's going to be finite. It's between 0 and 1. So obviously this is 0. And if I take something more than 1, this is what I have. Simple. If I look at this one, let's just look at this one. The first part, if I put x equals to 1, this is box 2, which is coming out as 2 because it's something more than 1, right? Signum this. Now this is very important. If this is 1, then this is minus 1/3, which is a negative number, and its signum is coming out as -1. So consequently, this is definitely not continuous. And obviously, if continuity is not there, so won't be differentiability. All right? Okay. So let's just take another problem. So exercise 7. So what you have been provided here with is the fact that f of x plus y is fx plus fy, and also an additional information that f dash 0 is equals to 2, and this is differentiable everywhere, and you are supposed to find out the original form of fx. Now this is very, very important, okay? Because once you see these things, there will be a very classic approach to these kind of problems that we are going to use, and we are going to use this again in the next class exercise as well. So if you have any problem with this approach in understanding what I'm telling you here, please let me know. So this is the first thing we have explored here, the basic first principle of differentiability. Now what you have here, simple. F of x plus y is fx plus fy. That is something I have used. And also fx is nothing but fx plus 0. Fx can be written as f of x plus 0. So very similar approach. So this is fx plus f0. All right. Consequently, this is getting cancelled. This is what you have. And this is nothing but f dash 0. Okay. The best part is we already know the value. Okay. So the first thing first, very simple definition of f dash x, and we have explored the rest of the relations provided by the equation, okay, and get the value. Now we have integrated both the parts, okay. Very simple, just use the antiderivative method. This is fx and this is 2x plus c, this constant of integration. So this is one method that we are going to repeatedly use for these kind of problems. I'll do another problem with you of this type. And so if you have any trouble regarding this one, then please let me know, because this is a very classic approach that we take for these kind of sums. Okay. So I hope this first part is okay. Once we are done with this is the basic relation we have. F dash x equals to 2. All right. So we have integrated both the sides. So this is what you have. Now the problem is you have already got fx equals to 2x plus something. You're supposed to find out fx, but the c is again here. So if you don't find out the value of c, your answer will not be complete. So this is what we are going to use now. So suppose I put x equals to 0. All right. So I'm putting x equals to 0. Then this is something I can write. Now let's just evaluate f0. So from this particular relation, I can write that f0 is f0 plus 0. Consequently, I can prove that this is actually 0. So using this one, it's a very simple thing. You can find out the value of c. So if c is 0, this part is gone and you're simply left with this particular part. So what is your answer? Fx should be equals to 2x. I hope this is okay with all of you. So if you have any trouble, please let me know. It's a very general approach to solving these kind of sums. It's literally everywhere. So in case you're having any trouble, you can let me know. All right. I'll do another sum of this type so that you people get a little comfortable with these types of manipulations. Okay. Let's just quickly go through what we can do here. Similar techniques. Now, just like this one, what we have done is this. So I can write x as x plus 0. So this is fx into f0. Rest is very, very similar, something we have already done. Now you know the value of f dash 0. So this, okay. So what you have is basically this one. All right. So I hope up to this portion it's okay. It's very similar to what we have done is in the previous exercise as well. So this is the first observation that we make. Then what we do is we simply go ahead and integrate. Okay. So that is the second step that we have also used for the previous one. This is the second step. We are integrating this. So if I integrate this, this will be ln fx. So even if you don't know the exact integration and what's going on, look at the antiderivative method. If I just differentiate this, look, using the chain rule. So log of something is 1 by that thing, and also the chain rule will suggest that you multiply it by its derivative. Okay. So if you integrate this, you will just get log fx, and 1 is very simple. This is x, and also you have this constant of integration. Fair enough. Now, again, once you look at the original thing that you need to find out, this is fx, okay? So you don't need this c. So just like the previous one, we have to find out what is the value of c, okay? For that, I'm finding f0. But unlike the previous one, you have this f0 equals to f0 into f0. So what are the possible options? Since fx is non-zero, this is very important. So f0 will be 1. This is very, very important. Why we are taking f0 equals to 1? Basically, f0 can be 0 or 1. But since it's non-zero everywhere, so that is why we have taken this 1. So just put x equals to 0. You will find out the value of c, and that is how you can find out what fx will be, because this is just ln fx is x, so this is e to the power x. I hope this is okay with all of you. If you have any doubts, please let me know. Okay. So again, very, very similar thing. So I want you people to get a little comfortable with this approach of solving sums, because sometimes when you see these kind of sums and you don't know which chapter it is from, relations or functions, don't know how to find out fx and all, this is one trick that we are going to use here. So let's just see. Again, as I have told you, whenever you are exploring the relation of including this function, obviously you have to manipulate fx or whatever is there in such a way that I can use this relation. So as you see, normally we write x plus h minus fx by h. Okay, so this is actually x plus h, this is fx. So we have just simply tried to manipulate this so that we can get this in the desired form and apply the given relation. Okay, I think I'm going to erase the ink so that you can see better. Very simple application. This f of x plus y by 2 is fx plus fy by 2. Algebraic manipulations. That's it. This is what you have. Simple. This is actually f dash 0, because this is actually nothing but 2h tends to 0. Sim. This is 0 plus 2h minus f0 by 2h. So this is what you have. So from all these complicated looking relations, you're just down to a very simple fact that f dash x equals to minus 1. So what you next do is simply integrate. So fx is, this is minus x. If you integrate this, this is minus x plus c. That's what you have. But at the end of the day, you need fx in terms of x, and the c is the constant of integration, which you have to get rid of. So for that, very classic technique that we have already used. So f0 equals to 1. So c equals to 1. I have already told you how to find out the value of f0, etc. So this is something I want you people to try and figure out. And consequently, you get the value of c. And as I told you, not all the cases will have the value of c as 0. So it's very important that you take some conditions and find out the value of c properly. In the previous two cases, you saw that c was 0, but here c will actually be 1 because f0 is 1. So if you put this as f0, will be actually, this is 0, so f0 is c, so c is actually 1. So this is something very, very important that you find out the value of c properly. All right. Okay. Last sum. You have to comment on the continuity and differentiability of gx. First of all, we are going to try and explore this with the graph. So this is the graph we have. Okay, simple things that we are using here. This is very simple for x less than 0. All right, x less than 0 means this side of the y-axis. So it's a straight line. It's like x minus 3. So this is the straight line that we have used. This is the straight line. Okay, and again, this is a parabola. It touches the meets the x-axis at 1 and 2. So I hope this graph is okay with you. If you still have any doubts, please let me know. Okay, so this is x minus 3. Okay, this is the straight line if it is less than 0, which is on this part of the y-axis, and on the positive part of the y-axis where x is greater than or equals to 0, this is the parabola that we have taken. All right, so this is the graph of fx. This is the graph of fx. What you need here is f of mod x and mod of fx. So let's just see those two graphs. This is f of mod x. Now this is very, very important. If I just see f of mod x, whatever be the input of x, ultimately it's coming out as positive. So if f is operating on something, that something is always positive. Okay, so look at this one. This is always positive as a non-negative. Okay, so this is the part of the graph that we are using. So that is why, as you see, this is the parabola, and also there is a replica, because it's an even function, and you know that even functions are symmetric about the y-axis. So obviously this parabola was already there for x positive. Now for x negative, we have a replica of this because this is symmetric. I hope this is okay with all of you. Still, if you have any problems regarding this graph, please let me know. And the next graph that we need to see is this. All right. So how the graph will look like? See this one. So if I take mod, so whatever was there, okay, if this was negative, this is just going to be positive. So look at this one. This was the original portion, but this is obviously in the negative zone where x is negative, y is negative, etc. But since the output is modulus of something, so we have taken the same thing, just the image, okay, just the image. So we have taken this, ultimately we are taking this mod of something. So same thing, but as you see the image with respect to the x-axis. So whatever was negative, the value is the same, just it's been transferred to the positive side. If you look at this branch, this is positive, this is also positive, but about this part of the branch, this is actually, you can see it's inverted. I hope this is okay with all of you. So look at the graphs individually, okay? Now let's see some points where we can talk about continuity and differentiability, etc. Look at this sharp bending. And also, this is pretty simple that there's a jump discontinuity in the graph. So these are the positions that we will consider when we are considering the ultimate continuity and differentiability. So see what we have written here. Okay, so what we are going to do is we examine the graphs individually and see that there are points x equals to 0, 1 and 2. Something I have already talked to you about in the previous slide. I'll just simply go back so that you can see this sharp bending. And also this is very obvious. Obviously there's a huge jump between the two graphs. So at x equals to 0, it's causing the problems in continuity. So that's it from today's class. So if you have any doubts regarding any problems, please let me know. And then we'll just do the class quiz quickly so that we are done with the class. Is there any problem or is there anything that you want me to repeat? I'm just quickly I'm going to go through the summary slides so that if you people have any problem in any concepts, you know, and also you'll get a recap of what we have done in this class. First thing first, that we started with continuity at a point, left hand limit, right hand limit, and functional value. Very simple. We extended the idea to an interval. Okay, I don't know, there's some problem with this particular image. Anyway, so open interval, closed interval, half open, half closed. And you know, consequently, what are the possible types of limits that we will use here, the right hand or the left hand accordingly. Algebra of continuous function. So first of all, we have taken this for points and then extended it for domains. Very simple. The sum, difference, product, scalar multiplier, quotient, all of them are continuous. But just for the quotient, be sure that you're not getting the denominator as 0. Some special functions which are continuous: polynomial, trigonometric, exponential, logarithmic, inverse function, etc. And also composition of two functions is also continuous. Discontinuity, this is very important. One is removable, where the limit is there but functional value is having some problem. If it's not defined, it is missing point. If it's defined but not equal, then it is isolated point. Okay, this is a removable discontinuity which can be manipulated in such a manner that the discontinuity is removed. But if the limit does not exist, then we have non-removable discontinuity. If they are finite but unequal, then there's a jump. As we talked about in the last class exercise, if you remember, there was a jump in the graph. So this kind of a problem is actually non-removable discontinuity of jump type. Infinite type you have also seen, as well as oscillatory type. Here at least one of the limits will tend to infinity, and in this case this will oscillate between two finite quantities. For example, sine 1 by x around x equals to 0. Differentiability, very basics, left hand limit, right hand limit, etc., the derivatives obviously. And also if it's differentiable, it's going to be continuous, but the converse may not be true. We have taken the example of x equals to mod x at 0 in an interval, very similar to what we do for continuity. Okay, you remember whatever extremities are included, you just check that one as well, you know, the left hand derivative or right hand derivative accordingly. Also, we have this final thing, which is the algebra of differentiable function. So this is very, very important, because all the product, quotient, you know, summation, subtraction, whatever you take, this will be derivable. But these are the counter examples that we have taken, that the converse is not true. So I'm just summed it up so that you people remember what we have talked about. And that's it.